In this section of the video, I'm just going to talk about when to use the z-table. Basically, there's two general sets of times when you'd use the z-table. One is when you're given a normal population and you're computing probabilities with respect to a value or set of values in that normal population. And the second is when you have a bell-shaped sampling distribution. The one we've talked about so far is the sampling distribution of x bar. There will be others as we move forward. So here was that first one, a normal population. You'll be given a mean, mu, and a population standard deviation, and you're talking about a distribution of x's. Please make sure when you draw these that you have the correct labeling, that it has x on the x-axis, and that you have mu and sigma for the parameters of the population. For sampling distributions, I'll talk here mainly in terms of the distribution of x bar, but again, there will be other sampling distributions as we move forward. Remember that we'll have a bell-shaped sampling distribution if the sample size is large enough, and also remember that it's going to be narrower than the population from which it was drawn, and it's narrower, or the way you can measure that is to take the standard error. You take the population standard deviation, divide by the square root of n. So here's just a picture then of a sampling distribution. Again, make sure that you have the correct labeling on the x-axis. Now it's x bar. It will be other things later, but it'll be different statistics. It's the distribution of x bars here. And so you have the mu, the mean of the x bars, which, as we know from last time, is equal to the mean of the population. And then you have the standard deviation or standard error of the x bars. And again, from the central limit theorem and last time, we know that that's going to be equal to the population standard deviation divided by the square root of n. So, what is a z-value? For a normal population, z is just the number of standard deviations between the mean and a specific point, or how many standard deviations away from the mean is the point of interest. For a sampling distribution, when you have a large sample size, which means the sampling distribution is normally distributed, z is the number of standard errors between the mean and a specific value of the sample mean. So for the normal population, the probabilities are z is equal to x minus mu over sigma. For example, if we have a population mean of 80 and a population standard deviation of 10, and we want to know the area between the mean and 80, or between 70 and 80, we just take x minus mu over sigma, 80 minus 70 over 10, 1 standard deviation, z is 1, we're 1 standard deviation above the mean. For a bell-shaped sampling distribution, z is equal to the sample mean minus the mean of the sample means over the standard error, the sigma of the x bars. I should hasten to add that this will not be the only bell-shaped sampling distribution we see, but this is the one we'll talk about now. So if you had a population mean of 80 and a standard deviation of 10, if n was 4, the mean of the sampling distribution is 80, the standard error is the standard deviation divided by the square root of n. So 10 divided by the square root of 4 is 5. You can see down at the bottom my sampling distribution has a standard error of 5 and a mean of 70. So z is equal to x bar. In this case, 80 is the x bar we're looking for. If we want to know, and then minus the mean of the x bars, which is 70, divided by the standard error. So z is 2. That means 80 is 2 standard errors above the mean. Okay, so in this video we're going to look at the mechanics of the z-table, particularly right now the looking up of probabilities based on z-values. So let's say obtain a z-value of 1.42, go down the left-hand side to 1.4, on the upper side of the chart go over to 0.02. Get the intersection, you have 0.4222, and you can look at the graph at the upper right. You can see we are from the mean to a point that's 1.4 standard deviations above the mean, that area is 0.4222. For minus 1.42, we look up the numbers exactly the same, but now we're looking at the area from the mean to a point 1.42 standard deviations below the mean. For 0.94, go to 0.904, look up the value. Now the area in the chart and the area corresponds to the area in blue up here. That probability is 0.3264. For 2.28, you can see that we have the area from 0, or from a point that's right at the mean, to a point that's 2.28 standard deviations above the mean. So what if z is 3.49? If you're looking at your z table, that's as far as this z table goes. Recall, the entire area above the mean is 0.5, and so when z is 3.49, the area from the mean to this point is 4998, which is nearly all of that 0.5. Hence, there's almost no chance of obtaining a point more than 3.4 standard deviations above the mean. You can see that here. We get to 3.4 standard deviations above. There's virtually nothing left. So continuing the z table to 3.6 or 4.2, it's going to go further out, but the probabilities are going to get from the mean to this point closer and closer to 0.5, and the area beyond very close to 0. Well, we're already at 0.0002 at this point, and that's virtually 0, and so that's where the table stops. Okay, in this part of the lecture, we're going to come back to z-table mechanics, but this time we're going to find z-values for percentiles. This is going to look backwards from what we've done before when we were looking at probabilities based on z-values. In other words, we're going to start from a probability in the center of the table and work our way back out to a z-value. So if we're looking at the 90th percentile, the upper graph you can see we're looking for a point below which 90% of the values lie. Well, we know 50% of those values are between the 0 going down, and so we're just looking at that upper part there, since the 90th percentile will be above the mean, and that area is 0.4, or 0.9 minus 0.5. So what we're going to do now is look in the center of the table and work our way out to a z to see how many standard deviations above the mean the 90th percentile will lie. So I'm going to find 0.4 in the center of the table. The closest number I could find was 0.3997. That's really close to 0.4. So now I'm going to go look at what column I'm in, what row and what column I'm in. I'm in the row 1.28 and the column 0.08. So that means that the point we're looking at right now, the 90th percentile, is going to be 1.2 standard deviations above the mean. Okay, now we're going to compute probabilities for a normal population. So first problem here, we have college textbooks, normally distributed, with a population mean that's mu of 76, and a population standard deviation, that's sigma of 1250. So given that, we want to know the likelihood of getting a textbook that costs less than $65. So we're going to sketch and label the distribution. Bell curve, label an X on the x-axis. You'll see that it's not always X, but for now it is. We're just looking at a population and values in that. And then we have mu of 76 and sigma of 12.5, and then we've shaded from 65 down. We're going to compute z. This is just like with the empirical rule. Just call it z now. Z is the number of standard deviations from the mean. Get the distance from the mean, 65 to 76, and divide it by the standard deviation. That means that this point right here, 65, is 0.88 standard deviations below the mean. That's all the minus means, is we're below the mean. So now we're going to use the z-table to find that probability. So I've got 0.8 and then 8 over here, so 0.88, and so the probability is 0.3106. Now remember, that probability is from the mean to here, to 65. We know from the mean down is 0.5, and from here to here is 0.3106. So when we calculate the area in the tail, we're going to take 0.5, the area below the mean, minus the 0.3106, the area between 65 and 76, to get 1894, which is the area below 65, the area that I have shaded here. Still have that normal distribution with a mean of 76 and a standard deviation of 1250, but now we want to find the probability that a textbook costs between 80 and 105. Again, we start with a sketch of the distribution. Mean of 76, sigma of 12.5, x is the label on the x-axis, and we're going from 80 to 105. So we're looking for this shaded area. Remember, we can only go from the mean to some point, so we'll have to go from the mean all the way out to 105. I didn't quite get that line far enough, but from the mean to 105, we can get that, and then we can get this area that I have the bar here, the greenish bar. So if we get all the way out to 105, and then we get this area from 80, then the area we're looking at will be the difference between those two. So the z for 105 minus 76, that's just the distance from the mean, divided by 12.5 to get 2.32 standard deviations from the mean. And for 80 minus 76 over 12.25, or 0.32 standard deviations above the mean. Then go look in your z-table, make sure you can find that for 2.32 you have an area of 4898, and for a z-value of 0.32, when you are 0.32 standard deviations away from the mean, you have encapsulated 0.1255, about 12.5% of the data. Then once you have that, you just take the difference between those. The 4898 minus the 1255 will give you 3643, which is the area in the dark blue that I have shaded there that we started with. For some reason, I just find that to be one of the funniest cartoons I've ever seen. So now we have another problem. The beck and call delivery service is normally distributed. The time it takes to deliver a package is normally distributed with mu of 43, sigma of 4, and we want to know then what proportion of deliveries will take less than 50 minutes. So again, sketch the distribution. Mu is 43, sigma is 4, population mean and population standard deviation. We're looking at x's. And we want to go from 50 down. So that's what I have here, just shaded in and everything. You can kind of see just by looking at this, the area on the left-hand side is 0.5, and then we're going to have to get a z-value and then find this area and add them together. Compute the z-value. 50 minus 43, the distance from the mean, divided by the size of the standard deviation. So we're 1.75 standard deviations above the mean. Then look in your z-table. For 1.75, you'll find a z-value of 0.4599. And then add that to 0.5, to get a total area of 0.9599. I'll pause a little bit on these, but if you need to hit pause to make sure you have everything down here, please do so. Okay, now we have, still says less than 50. This one should have been met less than 40. Okay, so same problem, but now we want to find less than 40. So this time we're going to find from the mean to 40 and then subtract from 0.5. So we compute our z. The point, remember, we can just go from the mean to some point. From 40 to 43 is 0.75, or about 3/4 of a standard deviation. The minus just means we're below the mean. Then go to the z-table. The minus, again, on the z-table, that doesn't make any difference. Just go to 0.75, and you'll find an area of 0.2734. That's the area that I have with the arrows over here in the curve. We're 0.75, and that area in there is 0.2734. Of course, from the mean down is 0.5, so we're going to subtract this from 0.5 to get our final answer of 0.2266. Okay, in this section we want to look at calculating the percentiles in our normal distribution. So for example, if you get a test score back and it says you're in the 90th percentile, that means that 90% of people who took the test scored lower than you did. So now we've got those college textbooks again, mean of 76 and a population standard deviation of 12.5. So now we're going to find the 90th percentile, the price below which 90% of the books fall. So we're going to draw and label. We have our mean and standard deviation, 76 and 12.5, just like before, x on the axis. And we're looking for a point above the mean where 90% of the values fall below this point. So we find the area from the mean. Now, so what that means is if it's 0.9 all the way down, and we know that from the mean down is 0.5, then this area here from the mean to our 90th percentile has to be 0.4. That's just the 0.9 minus the 0.5 is the 0.4. So now we're going to look in the z-table to go from this probability of 0.4 to a z-value. So this is like using the z-table backwards from what we've done before. So we go into the center of the table, and the closest number we're going to get to 0.4 is 3997, and then we're going to work our way out and find that goes to a z of 1.28. So again, go into the center or the body of the table, find a value that's close to 0.4, and they're in sequence, so you can kind of work your way down there. And the closest you can get to 0.4 is 0.3997, and then work your way out to a z of 1.28. So you can see here, I've gone into the body of the table, and I found 0.3997. That's the closest I can get to 0.4 in here. And then that's in the row 1.2, and in the column 8. So that's 1.28. So that means that the point over here that we're looking at, the 90th percentile, is going to be 1.2 standard deviations above the mean. So we just take the mean plus z, that's 1.28 standard deviation. So the 76 plus 1.28 times the standard deviation of 12.5 gives us a score of about 92. Or a price in this case. That's the price of a textbook. So if the book costs more than $92, you're in the top 10%. Although I doubt that's true anymore. I might have written this problem when the book prices were a little bit, let's say, less expensive than they are now. I'm kind of judging from my daughter's textbooks. They seem to cost more than that. Okay, so now back to the Beck and Call problem with the population mean of 43 and a standard deviation of 4. Now we want to find the 20th percentile, the point below which 20% of values fall. Now keep in mind, I know I've said this before, you can only go from the mean to some point. So we know that from the mean down is 0.5, and the point we're looking for is 0.2 down, so we have to find this area here is our first thing, and of course it's going to be 0.5 minus 0.2 is 0.3. And then that's what we're going to look up in the z-table, is 0.3. And the closest you can get to that is 0.2995. And you can see that goes with a z-value of 0.84. The reason I put the minus there is because we are below the mean. Okay, so the z will be negative because we're below the mean. Again, we're looking for the 20th percentile, but we don't have to get the area of 0.3 because that's from the mean to the point where we're at. And then once you get that, just look it up and you'll find this 0.84. So we can compute x. What I've done here on this first part, I've just written the formula for z, and then I've solved for x. Of course, you can reason this out. Z is the number of standard deviations from the mean, so we're going to go 0.84 standard deviations below the mean. So 43 minus 0.84 times 4, the standard deviation, will give us 39.64. That's the 20th percentile. Okay, now let's look at computing probabilities when we have a sampling distribution of the sample mean. Remember that distribution, that sampling distribution of the sample mean will follow a bell curve if n is large enough. That's that 15, 40, 100. 15, 40, 100. If you have skew, you need 15. Outliers, you need 40. Extreme values, you need 100. In order to have an n that's large enough to guarantee that the sampling distribution of x bar is a bell curve. It's the central limit theorem that we talked about in the last lecture. Remember that when you have the sampling distribution, you're going to have x bars wherever you had just x's before, but when you get to the standard error, you'll have to take the population standard deviation and divide by the square root of n. Did that last time. Sigma x bar is equal to sigma divided by the square root of n. You'll see that on the next slides as well. The rest of the calculations mirror those that we just used when we calculated probabilities for a normal population. Okay, so we have the time it takes, the population time it takes to deliver a pizza is 27 minutes. And with the population standard deviation of 8, what's the likelihood that the sample mean to deliver is under 25 if the sample size is 16. The reason I've highlighted sample mean and sample size is those are the key phrases that tell you we're talking about sampling distributions. The question is about a sample mean, and of course if you're going to get a sample mean you have to have some sample size. So that's different than the question we've been asking before. The other ones would have been what proportion of times are under 25. There would have been no sample. That's just a normal population and computing probabilities for that. For sampling distributions, it asks about the sample mean. Still going to start off with sketching the distribution. Note that on the axis now I have x bar because we're asking about sample means now, not x's. And the mean of the x bars is equal to the mean of the population, that's 27. And sigma x bar, the standard error, is what I just said a second ago, is sigma divided by the square root of n. So since our population standard deviation was 8 and our sample size is 16, the standard error is 2. So even though I really don't have this drawn to scale, if I had the population, it would be wider because the standard deviation is 8, so it would be a lot wider than this distribution that we have here. Well, anyway, you can see now we've got that all there, and then remember we can only get the area from the mean of the distribution to some point, so we want to get 25 below. I've got that shaded. We're going to compute z now to get the area that I have with my arrows there. X bar, that's the 25, minus the mean of the x bars, that's the 25. How far were we? This just mirrors the x minus mu on the normal distributions, but now we're talking about x bars, so it's x bar minus the mean of the x bars divided by the standard deviation or standard error for this distribution of 2. So 25 is one standard deviation below the mean of the whole population. Use the z-table to find the probability. You can remember back even to the empirical rule. Actually, if you look on the table, it's going to say 0.3413. I just did some rounding there to keep you remembering back that this is just the empirical rule right here too. We'll go plus or minus 1 standard error or standard deviation. We'll have 0.34 of the data, or half of 6/8. And then get the shaded area there, the distribution, 0.5, because that's from the mean down, minus this 0.34 will give us 0.16. If you're looking through the table, it's going to be 0.5 minus 0.3413, and you'll get 0.1587, which is pretty close to 0.16. So again, kind of compare this to what we did with just the normal population. Z is the number of standard errors from the mean instead of standard deviations. And pretty much wherever you had an x before, remember we had x minus mu, so it's x bar minus the mu of the x bars divided by the standard error of the x bars. You might want to get used to that kind of thing because we're going to have some other distributions where instead of being x bars here, it might be x bar A minus x bar B, or R, or P hat, or something like that. But they're all going to have this same kind of thing. Distance from the center of the distribution divided by the spread or standard error of the distribution. So now, historically, population mean, I'll just tell you, this problem right here is going to be sampling distribution just like the one we just did, except for I'm kind of moving a step closer to the basic philosophy of hypothesis testing and statistical inference, which is what we're going to be doing for the rest of the course. So anyway, historically the population mean number of items produced is 125 with a population standard deviation of 15. Last month, in a random sample of 25 workers, the sample mean was 134. First thing I'm just going to say is the sample size large enough. The sample size is 25, so it's large enough if there are no outliers. Skew's okay because 25 is larger than 16, but not okay if there are outliers because our sample size is less than 40. Okay, now to the real question here is, does that difference between the sample mean between 134 and 125, is that a true difference, or could it just be sampling error? That ought to sound familiar. Assignment 1, homework 1, the first few questions, we have this difference between a hypothesized mean and a sample mean, and we say it could be the difference, a real difference, or it could just be sampling error. Same thing with the binomial distribution. When we were looking at those last questions in each one, is this a surprising, could the percent or proportion that was proposed in the thing, is it plausible or not? Real or sampling error? And that really, well, that's the basis for, or the main idea of hypothesis testing, is we want to have some sense of whether what we observe is a real difference or could it just be sampling error. So here I've sketched everything out for this problem. The mean of the x-bars, or of the population, is 125. The standard error, standard deviation was 15, sample size was 25, so the standard error is 3. So looking at the calculations down here, sample mean minus the mean of the population mean of the sampling distribution, 134 minus 125, that's 9. That's 3 standard errors away from the mean. Now we can go all the way back to the empirical rule. If you go plus or minus 3, you've included almost everything. And if you look at 3 in this one, you're going to get 49.85. And that's from the mean to 134. So the area in the tail is 0.0015. And so using conventional cutoffs, usually 0.5, you'll see that used over and over again. This is a very low likelihood, it's very implausible that we would get a sample mean of 134 if the population mean were 125. So what we'll end up doing is saying that there's been a change. It's not 125 anymore. The population mean has gone up, because we would never get this result, or very rarely get this result, if the real population mean was 125. If you get that basic logic, then things are going to make sense for you. There's almost no chance that sample mean of 134 occurred by chance. It looks like things have changed, and as a manager, you know that you need to investigate the matter further. You'd like to know why it's gone up, and if you can keep it at this new higher level, maybe you need to reward people or find out what's happened. Maybe you've made some change and that's led to this, and so you'll know you want to keep going that way. But you do know that something's different. The population mean is not 125, it's higher than that. Okay, now I just want to wrap up, conclude, just kind of go back to the main points of what we've just gone through. We talked about when to use the z-table. We use it whenever we have a normal population or a bell-shaped sampling distribution, when n is large enough. Z-value, number of standard deviations from the mean if you have a normal population. If you have a bell-shaped sampling distribution, when n is large enough for the central limit theorem to apply, it'll be the number of standard errors from the mean. So for the population, it was z equals x minus mu over sigma. For the sampling distribution, it was x bar minus the mean of the x bars over the standard error, the sigma x bars. Make sure that when you get to that sigma x bar, it's going to be the population standard deviation divided by the square root of n. Went through some z-table mechanics, just going down the left-hand side and the upper side of the table to find, for example, a z-value for z equals 2.28. Also talked about doing that for percentiles, where we had, for example, the 80th percentile, so 50% below, so from the mean to 80 is 30%. or 0.3, go into the middle of the table, find the 0.3, find the z-value that, back out to the z-value, and then go that many standard deviations, in this case, above the mean. If you're looking for the 20th percentile, it'd be 0.5 minus the 0.2, so we have 0.3 between the mean and that point, and we'd still be looking at 0.3 in that case, but when we got to the z-value, it would be minus because we're below the mean. The 20th percentile is below the mean. Of course, the 50th percentile is exactly the mean. Then we computed probabilities for a normal population. This is extended what we've done previously with the empirical rule. So now we could get z-values that were not just 1, 2, and 3, and then find probabilities from that. Remember, we would calculate the z-value for 1 or 2 numbers depending on whatever we did. Make sure you shade the curve first. Just draw the graph. Make sure you have it labeled correctly, in this case with x, mu, and sigma for a normal population. And then just shade in the area and compute the z-values and the probabilities. Percentiles, now you start with your population, and we're looking for whatever, the 80th percentile or whatever. And in that section, we just went through those calculations. And then finally, we computed probabilities for sampling distribution to sample mean. Again, this is the center limit theorem, and this is really going to be sort of the underlying theory for much of what we do the rest of the course. So make sure you get this. When sample size is large enough, the sampling distribution is going to be a bell curve. In this case, when we went in the same kind of order as we did for computing probabilities for a normal distribution, but now z was the number of standard errors from the mean. When we drew our graph, the x-axis had an x-bar, because our random variable now is x-bar. Remember when we did the central limit theorem, we had that column of x-bars that varied from sample to sample. So that is our random variable now. And it's the mean of the x-bars, mu of the x-bars, and sigma of the x-bars. Then you pretty much proceed just like you would have when you computed probabilities for a normal population. And that concludes this lecture.